So Math 348, Mathematical Methods for Management, and we're starting a new subject, which is game theory. This is chapter 15 in Hillier and Lieberman. And subject is, how do you win a game? There are lots of games. The game can be selling more product than your competing company. Your army defeating the other country's army in a war. Your political campaign winning the election, and so on. So there's lots of games and lots of competitions, and we're going to study just a basic game in which there are only two opponents. So this is a two-person game. These are the only games we're going to consider. So there are two competing players or two competing adversaries. And in this game, whatever one person wins is exactly what the other person loses. So this is called a zero-sum game. So what this means is player one wins exactly what player two loses. Of course, a win can be positive or negative. So if player one loses $1,000, that means he's won minus 1,000, and player two wins, he loses minus 1,000, so that means he wins 1,000. So what player one wins or loses is exactly what player two loses or wins. And let's take the world's simplest game. So you have two players, and they each, at the same time, put out either one or two fingers. And if they put out the same number of fingers, player one wins $1. And if they put out different fingers, player one loses $1. Player one loses $1 means player two wins $1. You can also think of this in terms of you put out one or two fingers and you add up the number of fingers that are out there. It's either an even or an odd number of fingers. If the sum is even, player one wins. If the sum is odd, player two wins. And the way we describe this is by writing down a payoff table. So for this game of evens and odds, a payoff table looks like the following. So here we have player one. Here we have player two. And each player has a strategy. Strategy is what the player is going to do. And for each of player one and player two, there are two strategies. So strategy one is put out two fingers, or an even number of fingers. And each player also has the opposite strategy. Strategy two, you put out one finger, or an odd number of fingers. And let's say player one wins if the total number of fingers is even, and he loses otherwise. So here, for each player, we have a strategy. Strategy 1, strategy 2, strategy 1, strategy 2. And what I want to put in this table is the payoff. So if player 1 chooses strategy 1, he puts out 2 fingers. If player 2 chooses strategy 1, he puts out 2 fingers. The total number of fingers is even. So let's say in that case, player 1 wins $1. But if player 1 chooses strategy 1 and player 2 chooses strategy 2, 2 fingers plus 1 finger is 3 fingers, that's odd. Player 1 loses $1. What I'm putting in this table is the payoff to player 1. If player 1 chooses strategy 2 and player 2 chooses strategy 1, he puts out 2 fingers. Sorry, he puts out 1 finger. This person puts out 2 fingers. That's 3 fingers. Player 1 loses $1. If they each choose strategy 2, each puts out 1 finger. That's 2 fingers total. That's even. Player 1 loses $1. Sorry, player 1 wins the $1 because it's even. So this is the payoff to player 2. What's the payoff to player? Sorry, so this is the payoff to player 1. What is the payoff to player 2? It's a zero-sum game. When player 1 wins, player 2 loses. So in this case, if player 1 wins $1, that means player 2 lost $1. In this case, if player 1 loses $1, then player 2 wins $1. So I could write down the payoff table for player 2. It would just be each of these with a minus sign, each of these sign changed. But you get no more information. That is, if this tells you what player 1 wins at for each choice of strategies, it also tells you what player 2 wins at each choice of strategies. It's just the same number in absolute value, but with the sign changed. And the idea in game theory is to try to choose a strategy where you do the best. And there are 2 assumptions about our players. Right? And all the analysis only works on the basis of these assumptions. And they're very important. So assumption 1 is both players are rational. They'll each try to reason out what is the best thing to do. It's a rational game. Second, players, let me put it very simply, have no compassion for the other player. They just want to win. So players choose strategies only to promote their own welfare. So when we start to analyze our games, these are the hypotheses. Rational play, and all you want to do is win. Of course, maybe in some games you can't win, but then you just want to minimize your loss. So there is a prototypical example that will be used a lot in this chapter, and it is the following. So this is the prototypical example. So we have two politicians running against each other in an election, and they each want to win. That means they want to get the most votes. And it's coming down to the last 2 days of the political campaign, and they have to decide where they're going to spend their time. So in their city or in their district, there are two cities which the book calls Big Town and Megalopolis. And here's what they can decide to do. There are 2 days left in their campaign. Strategy 1 will be spend 1 day in each of the cities. Strategy 2 will be spend both days in one city, Big Town. Strategy 3 would be to spend both days in Megalopolis. And what is the payoff? It's you do one thing, that is player 1 chooses one strategy, player 2 chooses a different strategy, and you want to know, they both need to know, what is the payoff? The payoff is the number of additional votes they'll get by choosing one or the other of these strategies. So we're going to have 3 different scenarios of what could be the outcome of these 3 different strategic choices. And in the first of these, variation 1, we have the following payoff table. So here we have player 1 or politician 1, but we want to have a uniform way of talking, so we'll call them player 1 and player 2. And each of the players independently can choose one of the 3 strategies. So player 1 can choose strategy 1, 2, or 3. Player 2 can choose strategy 1, 2, or 3. And let's say we're going to measure the payoff in thousands of votes gained. So suppose if player 1 and player 2 both choose strategy 1, the gain is that player 1, the first politician, gains 1,000 votes. That is, if each politician chooses to spend 1 day in each city, the result in the end is player 1 will pick up 1,000 votes, and this is a zero-sum game. That means player 2 will have lost 1,000 votes. If player 1 chooses strategy 1, but player 2 chooses strategy 2, let's say in that case, player 1 gains 2,000 votes. And in this scenario, if player 1 chooses strategy 1 and player 2 chooses strategy 3, that means player 1 spends 1 day in each city. Player 2, the second politician, spends both days in Megalopolis. In that case, the first guy gains 4. That means 4,000 votes, and player 2 ends up with 4,000 votes less. So there's a swing of 4,000 votes. And let's just say these are the other numbers that are worked out by the campaign strategists, the campaign managers for each candidate. 1, 2, 4, 1, 0, 5, 0, 1, minus 1. So whatever was the method, the political campaign professionals for each candidate came up with this payoff chart on how many votes they would win or lose, depending on how they decided to spend the last 2 days of their campaign. Now, if you look at player 1, if player 1 chooses strategy 1, depending on what player 2 does, player 1 wins 1, 2, or 4,000 votes. If player 1 were to choose strategy 3, the numbers would be 0, 1, and minus 1. So in each case, no matter what player 2 does, player 1 does better choosing strategy 1 compared to strategy 3. Because in each choice of player 2's strategy, player 1 either wins 1 or it's a tie. Player 2 wins 2 or 1. Player 1 wins 2 or 1. Player 1 wins 4 or loses 1. So if you compare strategies 1 and 3 for player 1, in every possible case, he does better with strategy 1. So we can say, just looking at this table, for player 1, strategy 1 dominates strategy 3. In every possible case of what player 2 does, player 1 comes out ahead with strategy 1 compared to strategy 3. Because player 1 is rational, he will never pick strategy 3. He'll always do better no matter what, picking strategy 1. So we cross out strategy 3. Player 1 is never going to pick strategy 3. That would be irrational. And player 2, who's also rational, knows this. Player 2 can tell that player 1 will never take strategy 3. That's crossed off. So player 1, as far as player 2 is concerned, player 1 only chooses strategies 1 or 2. Now, player 2 is also rational. What do these numbers mean for player 2? It means in this case, player 2 loses 1,000 votes, and in this case, loses 1,000 votes. These numbers say what player 1 wins. Player 2, whatever player 1 wins, player 2 loses. Now, are any of these strategies really worse for player 2? Well, if player 2 chooses strategy 1, he loses 1,000. Let's say player 2 picks strategy 1. Player 2, if he picks strategy 1, he loses 1,000. If he picks strategy 3, he loses 4,000. If player 1 picks strategy 2, player 2 either loses 1,000 or 5,000. In both cases, he does much worse choosing strategy 3. He should never choose strategy 3. He can always do better choosing strategies 1 or 2. Never choose strategy 3. So in our new payoff table with strategy 3 for player 1 crossed out, Player 2 knows he can disregard this line. For player 2, strategy 1 dominates strategy 3. Because he'll always do better with strategy 1 than with strategy 3. Maybe he should choose strategy 2, but he should never choose strategy 3. So player 2 crosses that off. Okay. Now, of course, player 1 is rational. He reasons this out exactly the same way. He's never going to choose strategy 3. He knows player 2 is never going to choose strategy 3. So this is really the only payoff table. And when player 1 looks at this, he sees now 1, 2 compared to 1, 0. So now for player 1, strategy 1 dominates strategy 2. He'll always do better picking strategy 1 than picking strategy 2. So now player 1 crosses out strategy 2. He should never pick it. He should only pick strategy 1. And player 2 knows this. Player 2 knows now that player 1 is going to pick strategy 1. For player 2, there are only 2 choices. He'll either lose 1,000 votes or he'll lose 2,000 votes. Well, better to lose 1,000 than to lose 2,000. So he crosses that off. And this rational analysis leads to the conclusion that player 1 will choose strategy 1. Player 2 will choose strategy 2. And the best that they can do is they both spend a day in each city, and the first politician, player 1, will end up earning 1,000 votes. He'll have a net increase of 1,000 votes in his election total. So just by using this notion of one strategy dominating another, we figured out the best strategy for each player to use. If the players are rational and just trying to win, when they analyze what they should do step by step, this is the optimal strategy for them. There's no other possibility. Now, what made this analysis work is the fact that we had one strategy dominating another, but that doesn't always happen. In some sense, it rarely happens. So let's look at another payoff table for this situation. This is what we shall call variation 2. And in variation 2, the payoff table is the following. So here's player 2. Here's player 1. And again, they have the same 3 strategies. And now the payoff table is -3, -2, 6, 2, 0, 2, 5, -2, 4. Oops, -4. Now, What is player one going to do? Strategy one doesn't dominate strategy two or strategy three. Strategy two doesn't dominate either one or three. Strategy three doesn't dominate either of the other two. So in this case, with this payoff table, there's no dominant strategy for player one. And also, if you look at player two, I mean, suppose you look at player one chooses strategy one. He can win 3,000, lose 2,000, or lose 5,000. Well, he's better winning 3,000 than 2,000 or losing 6,000. On the other hand, here he loses 2,000, here he breaks even. Here he loses 5,000, but here he gains 4,000. So no one of these strategies for player two dominates. So in this case, no strategy dominates another strategy. So, and each candidate is fairly conservative. Each player is fairly conservative. You don't know what's going to happen, but you want to make sure you lose. In the worst case, you lose as little as possible. So let's look for player one and strategy one. What can happen to player one? He can lose 3,000 votes, 2,000 votes, or win 6,000. But what's the worst he can do choosing strategy one? The worst he can do is losing 3,000 votes. With strategy two, he can either win 2,000 votes or break even. The worst he can do is break even. So choosing strategy two, he'll never lose votes. He may gain, but he'll never lose. With strategy three, he could win 5,000, but lose 2,000 or 4,000. The worst he can do is lose 4,000 votes. And it's not like these are, this is a betting guy that he'll say, okay, I'm going to choose strategy one because maybe I'll win 6,000. No, they say to themselves, what's the worst I can do in each case? And in each case, the worst I can do is -3, 0, and -4. And I want to make the worst I can do as little as possible. So of these three strategies, which is the best one to pick? To maximize, so you lose the least possible amount in the worst case, and that's 0, right? Because of these three strategies, here in the worst case you would lose 3,000. Here you would break even. Here you would lose 4,000. So for each strategy, I choose the minimum. So this is, for each of these, this is the minimum. This is the worst I can do, right? The minimum amount that I would win. And I choose the maximum of all these, the maximum of the minimum. So if I choose strategy two, I know the worst I can do is break even. Any other strategy, the worst I can do, I would lose votes. So this is the max min value if I choose strategy two. Now, player number two analyzes this problem exactly the same way. Remember, for him, everything is opposite in sign. So -3, this means player one loses 3,000 votes, means player two gains 3,000 votes. So what's the worst what's the worst that can happen to player 2 if he chooses strategy 1? Can win 3,000, lose 2,000, lose 5,000. The worst that is he can do is lose 5,000. That is, if you choose the maximum number, that gives you the worst outcome for player 2. Here, the maximum number is 0. Here, the maximum number is 6. So in the worst case, with the first strategy, you lose 5,000 votes. With the second strategy, in the worst case, you break even. With the third strategy, in the worst case, you lose 6,000 votes. So the smallest of these numbers is 0. This you would call this is sometimes called the maxi-min. This is the mini-max. This is the maximum of the minimums. This is the minimum of the maximum. So player 2 can guarantee that the safest possible outcome is to choose strategy 2. So with this analysis, player 1 chooses strategy 2. Player 2 chooses strategy 2. And the net result, or the payoff to each player, is 0. So the goal for each player is to pick a strategy where you minimize your risk. And it turns out they both choose strategy 2, and they both break even. So in this case, where they both end up choosing exactly the same, with exactly the same result, this is called a stable game. This is the stable or equilibrium position. This position, strategy 2 for each player, is the minimum in its row and the maximum in its column. This is called a saddle point. This is just the terminology that's used in game theory. But in this game, there's a stable solution, there's a saddle point. And that's it, we're done. Okay, there's a third variation. Which I think I will talk about in the next lecture. But I want to do an example of how using dominant strategies can, when it works, give the optimal strategies for all our players, for both our players. So let me just, this is actually one of the homework problems. Let me just pause for 1 second. So this is problem 15.22. We have a 2-person zero-sum game. Again, with, for each player, 3 strategies. They don't have to be the same strategies for each player. It's just that each player has the choice of 3 strategies. And the payoff table is -3, 1, 2, 1, 2, 1, 1, 0, -2. So let's see whether there is a dominant strategy for player one. So for player one, choosing strategy 2 in every case gives a better payoff than choosing strategy 1. Here is +1 compared to -3. 2 is bigger than 1. I was wrong. This is not a dominant strategy. 1 is not bigger than 2. But 2 does dominate strategy 3. 1 is greater than or equal to 1. 2 is bigger than 0. 1 is bigger than -2. So it would be completely irrational for player one ever to pick strategy 3, because he would always do better picking strategy 2. So for player one, strategy 2 dominates strategy 3. So player one will never pick strategy 3, and player 2 knows it. So they just cross it, they both cross it off. Now, what about player 2? Player 2 now is just looking at this 2x3 table, and he wants to pick one strategy dominates another if the number in a given column is smaller than or is less than or equal to the number in any other column. So for example, choosing strategy 1 for player 2, in this case, he wins 3,000 votes, or he wins -3 compared to losing -1. Here he loses -1 compared to losing -2. So for player 2, see, this is telling you how much the person is going to lose, right? He'll lose more with strategy 2 than with strategy 1. So for player 2, strategy 1 dominates strategy 2, right? Here it's winning 3 as opposed to losing 1. Here it's losing 1 as opposed to losing 2. So player 2 is never going to choose strategy 2 when he can choose strategy 1. In fact, strategy 1 also dominates strategy 3, because here he loses 2 compared to winning 3. Here it's the same. He loses 1 or loses 1. So strategy 1 dominates strategy 2 and strategy 3. So that makes life easy for player 2. He's never going to choose strategy 2 or 3, only chooses strategy 1. And player 1 knows that. So player 1 knows that player 2 is going to choose strategy 1, and player 1 has 2 choices. He can either choose strategy 1 and lose 3, or choose strategy 2 and win 1. And of course, player 1 chooses strategy 2. So the best strategy for each player, player 2 chooses strategy 1, player 1 chooses strategy 2, player 1 wins 1, and player 2 loses 1. But that's the best that either player can do. There's no way that player 2 can do better than just losing 1, and there's no way that player 1 can do better than winning 1. So looking at the cases when one strategy dominates another, the result of this game is that it's the optimal strategy for both players is Player one chooses strategy two, player two chooses strategy one, and the net result is player one wins one, and in a zero-sum game, player two loses one. Okay. That's the beginning of our discussion of game theory.